looks like some people are not around. All right, back to screen share. All right, so the last thing we were talking about last week, we kind of ended with just a little bit of a mention of entropy, because entropy is a really big thing in terms of whether you're deciding if your reaction is spontaneous or not. So more letters of the alphabet, this time they're not Greek. We have, instead of an H for enthalpy, enthalpy, we have entropy, and this one is a capital S. And they define it as a direct measure of the randomness or disorder of a system. My house is a high entropy zone right at the moment with all the chaos that's going on with the renovation. So also things tend to progress naturally toward the disorder unless you use energy. So it's like, think about, your kitchen, you made dinner and you served dinner, or, it was on the table, and then the aftermath is all kind of the cleanup, because that requires energy to put stuff back the way it was prior to all of those things that you did. Entropy is basically what makes things be spontaneous. Okay, so think also about probability. All right, so I am down in the Hilltop area because this is where my office is, and it's a little after 5 here, so we're kind of sort of in the height of rush hour. So rush hour, relatively disorganized. Therefore, the probability of having a car accident at rush hour is statistically higher than having a car accident at 11 o'clock in the morning when there's not as much traffic on the road. So the two things kind of go together. If your probable thing is possible in many ways. I mean, you can have a fender bender, you can have a multi-car pileup, you can have rain that causes cars to slide into each other. Okay, all of those are different ways. Improbable events, like I said, this comes to mind just because I'm down in the Hilltop area of a couple of years ago, one of the FA-18s from Oceania crashed into a group of townhouses in the Bird Neck area. All right, so kind of an improbable event, even more improbable in that because it happened during the daytime, very few people were actually in the buildings. Nobody died. Okay, there were a couple of minor injuries and a lot of damage, but nobody died, which, okay, we're talking improbable, but it's also still entropy because something went wrong in terms of disorder in the system for the jet. So this gives you kind of things of, okay, car accident, okay, that's a fairly probable event. Airplane falling out of the sky, that's a less probable event. But both of those are kind of linked into the entropy idea. When we start looking at entropy in different states of matter, okay, solid, liquid, gas, we're going to turn a blind eye to plasma for a moment. Things that are more disordered, again, higher probability. Okay, gases are way more disorganized than liquids which are more disorganized than solids. General rules of thermodynamics of the universe, okay? Nature will spontaneously go toward the thing that has the highest probability. Way back pre-video games and all that sort of thing, thinking about, since I'm old, things that my brother and I played when we were little kids. One of those is pick up sticks. Think of it, if you have never really heard of that, think of it as it's like sort of like a bundle of, well, the ones we had were plastic, but I have seen wooden ones. For instance, if you had a bundle of wooden skewers and you hold them in your like hand so that they make a bundle, and then you sit the bottom edge on the table, and then you just sort of open your hand and let go. So they were really pretty organized when they were bundled together in your hand. The moment you opened your hand and let go, they kind of fall all over the place. Okay, so this is proceeding toward a much less organized state. There's an appendix in the back of your textbook that has 3 different columns, one of which got used in the first semester, which was the enthalpy, the delta H one. But there's 2 other columns which pop up in this chapter, which are entropy, and eventually we'll get around to Gibbs free energy, which is the G. So to give you kind of a standardized version of this, basically we want to limit our criteria when we're reporting these entropy values. They are usually given at 1 atmosphere and 25 Celsius. So kind of normal average, especially for around here, pressure and kind of warm day temperatures. You'll see the little S here with the thing that looks like a degree symbol. This is fairly consistent through both chemistry and physics, in that most of the textbooks use the little thing that looks like a degree symbol, which is also in math referred to as a knot, N-O-T. I'm not really sure why it's named that way, but sometimes you'll see it referred to as S naught, which doesn't make a lot of sense. You could just say standardized entropy. That kind of makes a little more intuitive sense. When we were doing enthalpy, Hess's law, and all those sorts of things in the first semester, one of the things that cropped up was that when you looked up the enthalpy values in the appendix in the back of the book there, some of them were positive and some of them were negative, and a few of them are 0 for things that are pure substances. If you look up the entropies in that particular chart, you will not see any negative values. Okay, this is because of the way we sort of interpret this data. We have similar units though. Okay, the units are really an awful lot like the H's that we saw, in that they're either joules per Kelvin or sometimes they are joules per Kelvin times moles. Both the Kelvin and the moles are on the bottom there. So nice statement here of, okay, solid has a little bit of entropy, liquid has more entropy, gas has much, much more entropy, which makes sense. Okay, think about it in terms of how the molecules bounce around in those states of matter, or slide around, or just kind of sit and vibrate, kind of like a car engine turned on. So if we talk about changes in states of matter, okay, melting, so we're going from a solid to a liquid. Vaporization, this one we saw a few chapters back, from a liquid to a gas. Both of those are situations where you had something that was more organized, and as the change is happening, you are becoming less organized. And the way that they indicate this, remember the little triangle is the delta, which means change in. Change in entropy is positive for things that are becoming messier. If we go in the opposite direction, if you have freezing, so from a liquid back to a solid, or condensation from a gas back to a liquid, this one's the opposite direction. So you're going to get less ordered to more ordered, and it gives you a negative entropy change. Anything that involves heat pretty much guarantees that you're going to have an increase in randomness, even if it's only a small increase. Think about old standards of us talking about temperature. We've got, okay, Fahrenheit, US stuff, which nothing of the rest of the world uses pretty much. We've got Celsius, we've got Kelvin. We know that Celsius has negative values, Kelvin doesn't have any negative values. So let's think about this in Kelvin units for a moment here. Okay, if you get down to 0, hypothetically, you have no randomness because nothing is moving. And I said hypothetically because this is this unachievable, or at least as far as we know, unachievable idea that even the electrons that are kind of sort of orbiting, SPDF orbitals, they would just sort of stop, kind of like taking a snapshot. And that way you would have no motion. Even if you only increase it a little bit, okay? What if you go from 273, which is pretty cold on the Kelvin scale, up to 283, okay, 10 degree increase. Probably not a big difference in terms of, absolute numbers here, but you are going to get more vibration, okay? So rotations and vibrations might be the extent of it if you haven't changed your state of matter. And I decided I would pick on dry ice for a moment because remember, dry ice is weird. Dry ice doesn't have a liquid form because dry ice is not really exactly ice at all. It's frozen carbon dioxide. If you go to the supermarket in the summertime, some of the supermarkets in the area carry dry ice for putting in your cooler for like packing things for shipping. It doesn't melt, it sublimates. It goes from a solid directly to the gas. So think about this in terms of entropy. Okay, we went from hunk, okay, of solid substance to gaseous state. That's a pretty big change in entropy. And in fact, it's a positive change in entropy because if you're going toward the gaseous state, you're going to end up with something that's a lot more disorganized. All right, switching gears just a little bit. New law of thermo. This one's called the second law of thermo. It kind of sounds a little bit incomplete the way it's stated, because we go entropy in the universe increases in a spontaneous process, remains unchanged in an equilibrium process. Well, it kind of sounds like they neglected something. It's like, okay, if it's spontaneous, it increases. What if it's non-spontaneous? You have to approach this from a little bit more big picture versus small picture, which, and this kind of pops up again. We saw a little bit of this back when we did original thermo stuff back in first semester of you have the universe is the everything, but we can separate it into systems and surroundings. So back to Zen physics, okay? The entropy in the universe as we know it is an ever increasing value, okay? Things are slowly getting more disorganized given time. And there is one theory that says when we get to the end of the universe, that you have kind of uniformly spread cold nothingness. Well, cold leftover molecules, because they're not doing anything, they're so cold. Like I said, sort of Zen physics idea. But we pay attention to specific things, either in a problem or in lab, okay? If you divvy it up into system versus surroundings, okay? So some people did lab for pH meter stuff last week. Some people are doing the lab for the pH meter stuff this week. So think about it this way, okay? The burette, the pH meter, the beaker in which you have your sample to which you're adding the stuff with your burette, that's your system, okay? Because we want to know how much we added, we want to track the pH, and we have to put it all in something, okay? The surroundings being the bench top, the other people in the lab, the air in the lab, the building, okay? All of those are part of the surroundings. So we can say that as a whole, if you add up both of those things, you get increasing entropy. So your entropy is positive. It's bigger than zero. And it's spontaneous. Basically, for those of you who have done the lab, you add the sodium hydroxide from your burette to the beaker. You stir it to make it more uniformly distributed, but if you just waited for a while, it would actually do it on its own because it's an acid-base reaction. Weak acid, strong base, but it's still an acid-base reaction. Here we have equilibrium, okay? This is kind of embraces the idea that everything in the system is kind of exactly equivalent and opposite to the surroundings. So think about it in terms of number. If you have +3 and -3, they're the same value, different signs, they give you 0. We can think about it as one has to be the opposite sign of the other one, okay? Doesn't necessarily have to be a negative. So like if your system was positive, that would make your surroundings negative. But you could also equally validly do it if your system was the negative one. So negative of a negative gives you a positive for your surroundings. It's just whatever the opposite value is. We can say that from a hypothetical point of view, if the entropy of the universe was decreasing, basically this means that your reaction is spontaneous in the reverse direction. It has to do with numbers, okay? The universe is never going to run backwards, okay? Or at least as far as we know, it's not going to run backwards. Although, back to Zen physics for a moment. if we had Big Bang, there is one theory that embraces something known as the Big Crunch, kind of like a rubber band, where if you stretch it as far as it will possibly go, and then you kind of reach the end of its limit and you let go and it snaps back. Okay, that there is a theory that this could maybe happen. I've read some hypothesis, big picture stuff, that there's a few people that say that there might be enough math to support that idea, but maybe. It's usually, oops, I scrolled too far down. It's usually things that are in the system that we are worried about. So therefore, they can be non-spontaneous, okay, or spontaneous in the other direction. It's also all kind of about the heat flow too. Okay, we've done some endo and exothermic kind of a little bit intermittently throughout the semester. We did a little bit when we talked about solutions. We did a little bit when we talked about heat of vaporization, those sorts of things. If it's endothermic, okay, you have surroundings giving heat to the system, okay, which from a human point of view, we think of it as getting cold. This also gives us a negative entropy value for your surroundings because the surroundings are losing the heat. If you have an exothermic reaction, okay, now your system is the one that's giving up the heat to the surroundings. So we can say that our entropy of the surroundings is positive or getting bigger. It really depends upon the direction, okay? Is it going into the system or out of the system? That will tell us the sign. If you want to figure out the number value, that also depends then on temperature. So here is a second law variation that accounts for entropy, enthalpy, and temperature. Okay. It's a way to use all the information that is mentioned in the second law verbally and sort of construct a usable equation from it. The higher your temperature, the smaller your entropy of surroundings. Because once you get up to a few thousand Kelvin, you're in a situation where your surroundings probably aren't noticing in comparison changes as much as if it were a cooler situation. We can use this whole spontaneity idea and entropy of the universe, tie the two together and go, okay, well, if it's positive, it's spontaneous. If it's negative, it's not spontaneous. Or more correctly, it's spontaneous in the other direction. All right, more variations. And this part of this chapter actually ties into the very last lab of the semester, which is not the wet chem lab, it's the borax lab. I haven't quite got all of the information for calculations and all loaded for that yet. It is an in progress thing. So I have the molar solubility information loaded, but I haven't finished the borax one yet. Partly because this time last year, by the time we got to molar solubility, and we usually do the borax lab, yeah, this time last year, once we finally got to that final titration lab, which we did as like a demo, we kind of went, yeah, we're not even going to do the last one. So this year we're going to do it, but it's going to be data and hopefully a video. We'll see if I get if I can find a good video, or if I can make a video to kind of show you what we're looking at in terms of the borax lab. All right, entropy, enthalpy, temperature. And there's another letter of the alphabet thrown in, which is the G. So the first version of this equation, I'll refer to it as the less useful version. It's not unuseful, it's just not as useful as the kind that has all the deltas in it. GHTS. We haven't seen the G before. The G is known as Gibbs free energy. T's got to be in Kelvin because we want to make sure that we don't have a possibility of negative temperatures, because that would change things a great deal in the wrong way. And S is our entropy. If you aren't changing your temperature, basically you reach a particular temperature and you leave it there. And this is actually the way the lab works for the borax. There are 6 temperatures that this particular little reaction of dissolving the borax and then titrating it is supposed to work at. There's a as close to 0 as we can get, which usually involves an ice bath. There's a room temperature one. There's a barely lukewarm one, and then there are 3 other warmer ones. But we use a water bath when we do this lab. We take a giant test tube and stick it into the water bath and let it come to equilibrium. And then we do the titration. So this makes use of this idea, that we're only looking at a particular temperature when you're analyzing this data. So here is your more useful version. Delta G, so change in Gibbs free energy, is based upon change in enthalpy minus T change in entropy. You get 3 possibilities. Is it negative? Is it positive? Is it basically 0? Sometimes it's not exactly 0. Sometimes it's a small number. If your G is negative, we're going to say spontaneous. If your G is positive, we're going to say non-spontaneous. If it's approximately 0, we're going to say that it's at equilibrium. And actually, I left a letter out. It's supposed to say equilibria. All right, my weird word here. I am a sci-fi buff. TANSTAFL is one of those acronym words where each letter of the alphabet stands for a word. There is a book written by a guy who's dead now, named Robert Heinlein, known as The Moon is a Harsh Mistress. And this particular book, in some ways, revolves around the Earth having established a colony on the moon, which, considering we actually landed on the moon and people walked on the moon in the late 60s, and now here, like half a century later, we still don't have a base up there yet, is kind of a little bit head scratching. But think about this, okay? The moon essentially has almost no resources, okay? There's no air, there's no plant life, there's some minerals, which you could turn into some usable things based upon reactions. But because there's not even any atmosphere, that means you actually have to pay to breathe. Okay. So Tanstaffel, there ain't no such thing as a free lunch. Okay. Meaning that nothing in terms of thermodynamics also occurs without an energy exchange. Because remember, think about all the things we've done for equilibrium. Equilibrium doesn't mean no change. Equilibrium means no net change. If you turn on the faucet and you have kind of a slow running sink, and you don't turn on the faucet full blast, you'll eventually reach this sort of state where there's probably a gallon or two of water in the sink, and some of it's flowing out at about the same speed the faucet is dumping more water in. It doesn't mean no change. It means no net change. And since I'm missing a lot of people, I think I'm probably going to kind of end with my last example here. All right, mercury, Hg, has an enthalpy of 58.51 kilojoules per mole. These are numbers from the back of the book. It has an entropy of 92.92 joules per Kelvin mole times moles. Now, okay, look at your units, okay? Beware of your units and the fact they do not match. If I want to figure out mathematically what my boiling temperature is, I am going to use that third situation there. I am going to use the idea that if I am at equilibrium, because remember, boiling is the vapor is going up at exactly the same speed at which the gas is coming back down, and you have vapor pressure and atmospheric pressure equaling each other. So that means both the liquid and the gas have to have the same free energy. That's why we're going to set it to 0. It also means we can scoot our reaction around. Okay. If my delta G is 0 and I scoot everything over to the left, okay, then I get delta H and negative T delta S. And I also realized I left out a negative sign. Okay. There's supposed to be a negative there. Otherwise, my negative signs don't cancel out the way they're supposed to. Yeah, I didn't realize I forgot one. Rearrange it. Also correct your enthalpy so that it's in joules per mole like your entropy. So instead of having 58.51, I've got 58,510 over my 92.92. And then finish your math. If you left it in Kelvin, it's going to be about 629.5. If you subtract your 273 and give it in Celsius, you end up with about 356.5. So we have a couple more thermodynamic laws to deal with. We have a couple more variations on this theme. So we're about a bit more than halfway through this chapter. Just to give you a little bit of a thought about what's sort of up and coming here for the next few weeks. So Thursday, we'll go over homework from KSPs and buffers. We'll probably do a little bit more thermo. I may not finish thermo because I don't want you to do homework the weekend that we have a test. After thermo, we have electrochem, of which we're going to cover most of that chapter, with the tail end of it being sort of not as well covered as the beginning part. And then there's one more chapter we're going to do highlights of, which is nuclear. Okay. We're not going to do the whole nuclear chapter. We're going to do kind of bits and pieces of it. So basically we have rest of thermo, more or less most of electrochem, and a little bit of nuclear. And that's the end of the semester. So the end is in sight. Remember also, there is a fourth test, which will cover those last three chapters, thermo, electrochem, and a little bit of nuclear. That's your fourth test. Remember, if you take all four of them, you get to drop one. If you missed one, that's just the one that gets. And then the final exam will be I'll probably, that one I'm probably only going to be able to give you a 2-day window for. My Google Calendar and make sure I'm quoting my dates correctly here. You will probably have the 5th and the 6th. It'll probably cut off at midnight on the 6th because I have to turn in grades on the 7th. Lab stuff is due at the beginning of the week. Lab stuff is due on the 3rd because I need basically the 3rd and the 4th to work on all the lab stuff and finish that before I have to grade the final exam, which of course is on Canvas because everything is on Canvas these days. Questions? Some of you I will see tomorrow night in lab. Some of you I will see one more time the following week. And then the final week is the rest of the molar solubility stuff. All right, I will see some of you tomorrow.